Okay, this video is going to talk about zeros of polynomial functions. And if we're going to talk about a zero, we're going to talk about a zero's multiplicity. So what does that mean? Well, let's get a working definition of what a zero is. So we say that a number C is a zero of a polynomial function. And I'll call it P of x if, when I evaluate P at C, it gives me the number 0. So example, let's let P of x be x squared minus 2x minus 15. And you get asked, what are the zeros? If any. Okay. Well, what this is not, you're not being asked to find P evaluated at 0. That's a different concept altogether. Because if I evaluate P at 0, then wherever's in x, I replace it with 0. And then these terms go away, and I'm left with negative 15. That's a question like, what is the y-intercept? The y-intercept is found at the constant term, which is found at evaluating your function at 0. Okay, now all that in red is not what is being asked if you're asked what are the zeros. And students often get that confused, mixed up. So what are the zeros of that? Well, to find the zeros, then I'm going to set the polynomial equal to 0 and solve it for x. Now, right now, this polynomial is in standard form. It's not in factored form. And when it's in standard form, it's not very easy to solve that. I could solve that by using quadratic formula. I think an easier way to solve it is to factor it. Are there two numbers that multiply together to give you negative 15? At the same time, they add up together to give you negative 2. And yes, negative 5 and positive 3. And so we can see straight away when it's in factored form, what's going to solve this? Well, if x is 5 and if x is negative 3. Because if x is 5, it's going to make the whole thing equal 0. So my zeros are 5 and negative 3. And in fact, what is P evaluated at 5? Well, if I do it directly, it's going to be 25 minus 10 minus 15, which is 25 minus 25, which is 0. And this fits the definition of what a 0 is. 5 is a 0. And we could see that here when we factored it. Similarly, negative 3 is a 0. So I have two zeros, 5 and negative 3. Notice that the degree is 2, and I had two zeros. So that's not a coincidence there. Okay, so when it's in factored form, it's easy to see the zeros if our polynomial is expressed as a product of linear factors. Okay, so if you're given that and you're asked what are the zeros, well, we can see if I set this equal to 0, what will solve it? If x is 1, that'll make the whole thing 0. If x is negative 2, make the whole thing 0. So the zeros are 1, negative 2, and 7. Okay. Now, if it's expressed as a product of linear factors, that's easy to see. Okay. What if it's not? What if it's only partially factorized? Okay, well, that is linear. What is inside there is not linear. So if I'm going to see what all the zeros are, I need to get it into linear factors. So once again, we just factored this earlier, and that turns out to be x minus 5 times x plus 3. But we've got this power on the outside, and so this will apply to each thing inside here. And then I can combine those. That's going to be x minus 5 to the 3 plus 3 to the 6th power. Now I've got linear factors, and now it's easy to see the zeros. I put it equal to 0, and I can see that 5 is a 0, and I can see that negative 3 is a 0. Okay. Now, 5 is repeated 6 times, so that's our multiplicity. So 5 is a 0. And its multiplicity is how many times it's repeated, because x minus 5 all to the 6th power is x minus 5 times x minus 5 times x minus 5 6 times. And here we can see negative 3 is a 0, and its multiplicity is 3. Okay. Now, that's all well and fine. What does multiplicity have to do with anything? Well, the following statements mean the same thing. Okay. C is a 0 of a polynomial. Okay, well, the definition of a 0 is that P evaluated at C is equal to 0. If C is a 0, then the point C comma 0 is an x-intercept. We're assuming here C is a real number. And finally, if C is a 0, that means the same thing as x minus C is a factor. Okay. So if I've got something like that, then you can see what are the zeros. Well, if I set this equal to 0, we can see negative 2 is a 0 and positive 3 is a 0. Okay. Now, what about the multiplicity? The multiplicity of negative 2 is 1, and the multiplicity of 3 is 2. Okay. But negative 2 is a 0, means the same thing as x minus negative 2 is a factor, and you can certainly see that x plus 2, x minus negative 2 is a factor. 3 is a 0, x minus 3 is a factor of p. Okay, and of course if I evaluate p at negative 2, now I don't even, okay, if I go back and evaluate p at negative 2, everywhere there's an x, replace it with negative 2, it's going to give me 0. And if I evaluate p at 3, go back and replace a 3 everywhere for x, I'd get 5 here, but then I get times 0. Okay, so all of those mean the same thing. So on the graph, I'll have an x-intercept at negative 2 comma 0, and I'll have an x-intercept at the point 3 comma 0. Now we're going to put multiplicity in it. So suppose c is a 0, then that means the same thing as the point c comma 0 is an x-intercept on the graph. If c has odd multiplicity, then the graph of your polynomial p crosses through at your x-intercept 3 comma c comma 0. If your 0c has even multiplicity, then the graph of p of x will touch and bounce back. So it touches and bounces back or turns back at the point c comma 0. Okay. All right, so let's see what's going to happen. All right, let's have a look at this. Let me make it a little bit smaller so I can get it in here. Just, okay, try it again. I'm hoping to get it all in one frame. Okay. All right, that should be good enough. Okay, now it wants to know what the zeros are. Remember, if you have a 0, if you have an x-intercept, that's a 0. So I can see that my zeros are going to be, I have an x-intercept here at negative 9, and I have an x-intercept at negative 7, and I have an x-intercept at negative 2, and I have an x-intercept at 3. Okay, so the zeros are going to be negative 9, negative 7, negative 2, and 3. Okay, so let's just go from left to right. So my 0 at x equals negative 9, what kind of multiplicity will that have? Will that have odd or even? Well, the graph crosses through, so it will have odd multiplicity. At negative 7, it crosses through, so the multiplicity will be odd. At -2, it touches and bounces back, so it will have even multiplicity. And at +3, the graph crosses through, and so the 0, 3 will have odd multiplicity. Now, what else can we say if we're going to try and answer these questions? Well, what does the end behavior have? It has end behavior down up. Now, if it has end behavior down up, so this is from a previous lesson, what is the leading term? Well, the leading term is a positive number times x to an odd power. And if you have the leading term, you automatically get the degree. That's your degree. So the degree is going to be an odd number. I don't know what it is exactly. And the leading coefficient is going to be a positive number. Okay, so that's how I would fill that one out. Okay. So let's get back to this, and we might do a couple of others. So let's see if we can. Okay. So I'm going to need to, have some reference point here, some grid points. Let me make that black. Okay, and let's have this at -2, -1, 2, and 3. Okay, so this is my polynomial function p. So what are the zeros? Well, I can certainly see what the real zeros are, because if you have a real zero, you get an x-intercept. So the answer is I have a 0 at -2, at -1, at 2, and at 3. Now, what can we say about the multiplicities? Well, at -2, the graph crosses through. So -2 will have odd multiplicity. So it's only repeated once, or it's repeated 3 times, 5 times, etc. What's happening at -1? It's touching and bouncing back. So -1 will have even multiplicity. What's happening at 2? Well, it's crossing through at 2, so it will have odd multiplicity. What's happening at 3? It's touching and bouncing back, so it has even multiplicity. What can we say about the degree? And what can we say about the leading coefficient? Well, we can see that this has end behavior, down, down. And if it has end behavior down, down, then the leading term is going to have, the leading term is going to be a negative number times x to an even power. So this is telling me that the degree is going to be an even number, and that the leading coefficient is going to be a negative number. Okay. So now if we go back to this original problem that we had at the beginning, All right, so what are the zeros? And we see, well, I have a linear factor there. This one, are there two numbers that multiply together to give me negative 10, but at the same time add up together to give me positive 3? And yeah, positive 5 and negative 2. 5 times negative 2 is that, and 5 plus negative 2 is positive 3. And so this is going to now be x plus 5 squared and x minus 2 squared. And then I can combine these, and that's going to be x minus 2 all cubed. Now I can see what the zeros are. The zeros are going to be 2 and negative 5. What are the multiplicities? The multiplicity of 2 is 3. And that means the graph will cross through the x-axis at 2. Because 2 comma 0 will be an x-intercept. Now what about negative 5? It has multiplicity too. Since the multiplicity is even, the graph is going to touch and bounce back. The x-axis at negative 5. Okay. There